When we cannot see, we are forced to grope in the dark. The cathode ray tube gives sight to electronics. Cathode ray tubes come in many forms, large ones, small ones, all sizes in between. Some are round, some are square, some have unusual shapes. These are the eyes of radar. This is the tuning eye of a radio receiver. This is the picture tube or kinescope of a television set. This is the indicator tube of a precision laboratory oscilloscope. These are the windows to electronics. All are cathode ray tubes. All work on the same principle. A beam of electrons traces a pattern of light on a fluorescent screen. It is fairly easy to move this electron beam. A magnet will bend it. A voltage applied to an element inside the tube will deflect the beam. The electrons in the beam travel at almost the speed of light. Because they have no inertia, they can be moved either slowly or at a very rapid rate. Let's take a closer look at the cathode ray tube, or CRT as it is often called. This tube is an evacuated glass container or envelope. Inside is a device which generates the electron beam called the gun. A fluorescent material gives off light when struck by the electron beam is called the screen. Many cathode ray tubes have elements for moving the beam called deflection plates. The gun consists of 3 or more elements. Its heart is the oxide-coated cathode. When heated by the filament or heater, the cathode gives off electrons. Around the cathode is an element called the grid. This controls electron flow. Electrons have a negative charge. A plate or anode will attract the electrons when connected to a positive voltage. All of the electrons do not strike the anode. Some of them continue on through a hole or aperture in the plate and become the beam current. Since only part of the electrons go through this opening, the beam current is always less than the total cathode current. It is the beam current that produces the light on the screen. All the rest is wasted. The designer of the tube tries to get as high a ratio of beam current to cathode current as possible. Extra elements in the gun focus the electrons into a sharp spot as they hit the screen. These elements are called focusing electrodes. In a television picture tube, the beam often is focused and almost always deflected by a magnetic field from a coil around the neck of the tube. This is called magnetic deflection. Magnetic deflection works well enough in a TV set, but it can't give the wide range of deflection speeds needed in a precision cathode ray oscilloscope. CRTs used in an oscilloscope have special deflection elements or plates inside the tube. These plates provide what is called electrostatic deflection. A voltage on one set of plates will move the beam up and down. A voltage on the other plates will move it back and forth. In many high voltage tubes, you'll find a metallized layer over the fluorescent phosphor. This layer, like a mirror, reflects most of the phosphor's light forward toward the viewer, increasing the brightness and the contrast. This metallized layer keeps charges from building up on the screen, charges which might distort the pattern of light. Here we have a complete cathode ray tube. A gun assembly consisting of a heater, a cathode which gives off electrons, and a grid to control the flow, focusing electrodes, an anode with an aperture that lets the beam current pass on to the fluorescent screen, vertical deflecting plates, an interplate shield, and the horizontal deflecting plates. Many tubes also have a post-accelerating electrode. This is a band connected to a voltage more positive than that of the anode. This voltage attracts or speeds up the electrons even more. The faster they move, the more light they give when they hit the screen. In the precision instrument type of cathode ray tube, this post-accelerating element is often in the form of a continuous spiral, or helix, made of resistive material. This helix accelerates the beam more uniformly and with less distortion than if just one or more post-accelerating bands were used. To see how precision instrument-grade cathode ray tubes are made, let's visit the tube department of Tektronix Incorporated in Portland, Oregon. At Tektronix, we manufacture laboratory-type oscilloscopes. The accuracy of these instruments is dependent on the precision built into the cathode ray tube. This tube is literally the heart of the oscilloscope. We manufacture a wide variety of oscilloscopes to meet the needs of industry, research, and education. Different tubes are needed to get the maximum performance from each instrument. Tubes of different sizes, of different lengths. Tubes with 2 or more electron guns. Tubes to be used to display extremely high-frequency waveforms. Each tube requires special handling and offers special problems in the manufacturing. For our trip, let's follow one of the more common types of tubes through its manufacturing processes. The precision, the performance, and even the life of the cathode ray tube is dependent on the quality of the components which go into its construction and upon the care and accuracy of their assembly. Most of the gun parts are made of stainless steel or of nickel. This material is carefully inspected. It comes to us as flat strips or as wire. The wrong thickness, improper alloys, or certain impurities could cause trouble in the finished tube. The metal is drawn, it is punched, or it is bent to form the various parts. Accurate size and shape is important. To remove the rough edges of the newly formed parts, we burnish them by tumbling in a soap solution together with small stones. In each side of this tumbling barrel, there are about 250 pounds of stone and 10 pounds of parts. All of them, even the smallest wires and parts, are tumbled and burnished. This operation relieves the stresses and strains within the formed parts. Assembly of the electron gun gets underway with the welding of the support wires and tabs to the metal parts. Here, the supports are being welded to a vertical deflecting plate. The pressure, the current, and the time is important if we are to get a strong weld without warping or distorting the part. Each part is inspected carefully. Deflection linearity of the finished tube depends on the size and shape of these parts. Every plate is measured. Each must be accurate to 1/10,000th of an inch. This machine is doing what used to be a hand operation, spot welding the support wires to the grid cup. Done by hand, the job was slow and a production bottleneck. Not only is the machine faster, but it turns out more uniform assemblies. Here the supports are being welded to a split type of focusing anode. We have built all of these machines ourselves. Connections must be made to the various tube elements through the walls of the glass envelope. Here you see a glass bead being sealed to the metal deflection plate pin or terminal. The glass is completely fused to the metal. The pin is made of a special alloy which expands at exactly the same rate as the glass. A temporary support ring is welded to the deflection plate terminals. This ring will ensure the proper alignment and spacing of these pins during the rest of the process. It's extremely important that the parts be clean. Ultrasonic agitation is used in an alkaline detergent solution. They are rinsed several times in filtered deionized hot water. Pure acetone is used as a final rinse. To remove any impurities trapped in the pores of the metal, the gun parts will be fired at 1,000 degrees centigrade in a hydrogen atmosphere. The oxide-coated cathode, which generates the electron beam, is the most important single element in the tube. Pure nickel with traces of certain other elements make up the cathode cylinder. It is supported and insulated by a ceramic ring. We must handle these parts very carefully. The light output of the finished tube, even its very life, depends on the purity of the materials and the manner of their assembly. To clean the cathodes, we boil them in a solution of sodium cyanide, 60 cathodes in a batch. The cathodes have been hydrogen fired at a temperature of 750 degrees centigrade. This has taken a total time of 12 hours. They are stored in glass jars with a drying agent to make sure that they stay clean and dry until ready for further processing. The basic materials used in the cathode coating are barium, strontium, and calcium carbonates. These carbonates will be converted to oxides during the later processing. Traces of magnesium, aluminum, zirconium, or silicon in the nickel will activate the cathode coating. 24 cathodes are placed behind the small holes in this disc. Magnetic agitation is used in the spray gun to keep the material in suspension. Nitrogen at 20 pounds pressure sprays the material. Building up the proper coat takes about 30 revolutions of the disc. On every other revolution, the flow of material is cut off so the coating may dry. Thickness of the coating is important. It may not be less than 24 ten-thousandths of an inch thick, or more than 29 ten-thousandths. We check the thickness and apply additional coats if needed. Each cathode is checked to assure that it has a uniform coating. Any loose material is brushed away with a fine sable hair brush. A connecting lead is welded to the cathode. The assembly is never touched by the hands of the operator. Tweezers or finger cuts are used. The cathode is assembled in the grid cup. A spacer assures proper separation. The grid to cathode spacing is checked. It is within the proper tolerance, so the assembly is spot welded in place. An additional ceramic insulator has been installed. This will provide terminal connections for the heater. A connecting lead is welded to the grid cup. The coiled heater is inspected and placed inside the cathode sleeve. The heater leads are welded to the terminals. Permanent, accurate alignment of the gun parts is best assured by fusing them into 4 glass rods. Pyrex glass gives the best dimensional stability, but because it's such a good insulator, it tends to pick up electrostatic charges which sometimes distort the trace. To overcome this problem, we lightly coat the Pyrex glass with lead oxide. During the process that follows, a microscopic layer of lead glass is formed on the outside of the rods. Charges do not build up on this treated glass. The gun parts are placed in a jig. Accurately ground spacers are placed between the various parts to assure their alignment. The jig clamps the parts in position. 4 of the prepared glass rods have been placed in this machine. Vacuum holds the rods in place. Gas flames soften the glass. The metal mounting tabs are forced into the soft glass. As the glass cools, the gun assembly is held in permanent, accurate alignment. Let's watch another cycle of the machine. Rods are placed in position for the next operation. This machine, which fuses all 4 rods at once, places much less strain on the assembly than the older method, which fired only 1 rod at a time. Here we have a complete electron gun assembly. A grid cup containing the oxide-coated cathode, a first anode, focusing electrodes, a second anode, the vertical deflection plates, an interplate shield, and the horizontal deflection plates, all permanently mounted and aligned by 4 glass rods. Proper alignment and spacing of the gun parts is assured by checking on an optical comparator. An enlarged image of the assembly is projected on the screen. It is easy to check the dimensions within a fraction of a thousandth of an inch. The stem assembly or header is placed in one end of a jig. The gun is placed in the other end. The interconnecting leads are welded. Interconnecting wires, tabs, and shields are welded into position. This is a shield for the vertical deflection plate. Tweezer-type electrodes are used to make these welds. A pre-cut length of glass tubing is placed over the gun assembly. We are now ready to seal this to the stem. This is an automatic sealing machine. Flames preheat the glass. Hotter flames soften the glass. The glass of the neck and the glass stem are fused together. Excess glass drops off. This completes the seal. The assembly is placed in an annealing oven to equalize any stresses or strains in the glass. Again, the gun is carefully inspected. The deflection plate spacing is measured. And now the terminal assembly is welded to the deflection plate leads. A cardboard shield prevents metal from being splattered on the plates. This completes the work on the electron gun assembly. The glass envelope or bottle has been carefully cleaned and inspected. First, we apply the resistive post-accelerating band or helix. This resistance material, or ink as we call it, is ruled onto the inside surface of the glass. This resistance material consists of several different types of carbon, together with suitable binders. Materials in the ink etch or slightly dissolve the glass in order that it will make a firm bond to the envelope wall. It is continually agitated to prevent settling. It flows to the pen through a small, flexible tube. The ruling point is much the same as the tip of a ballpoint pen. It must be changed often, as both the ink and the glass are quite abrasive. We must have a constant surface speed at the point of ruling if we wish to get a uniform resistance coating. The diameter of the envelope varies from one end to the other, so we must change the machine speed as the winding progresses. A small wheel is placed on the outside of the glass just over the ruling point. This wheel is coupled to a tachometer-type generator. A voltage is generated and is applied to a thyrotron tube. This controls the speed of the main drive motor, assuring a constant linear surface speed at the point of ruling. The ink is dried with warm air in an oven. Each bulb is inspected and a resistance check is made. The resistance varies from 150 to 600 megohms, depending on the type of tube being produced. We are now ready to apply the fluorescent screen or phosphor. Many different types of screens are used. The most common screen materials are crystals of highly purified zinc sulfide or zinc silicate with slight traces of copper, silver, or manganese as an activator. Potassium silicate is used as a binder. A solution of deionized water and barium acetate is poured into the bottle. This acts as a cushion through which the heavier screen materials will settle. In 1 hour's time, the screen material is settled as a uniform layer onto the faceplate. We must handle the tube very carefully at this point. We don't want to disturb the phosphor. The bottles are gently tipped and the excess liquid is poured off. The screen is very fragile. It must be dried before any further work is done on the bottle. It is dried as it travels on the conveyor. A careful inspection to locate any flaws in the screen. We are now ready to apply the metallizing layer. It is not practical to apply it directly to the phosphor. This would produce a rough, non-uniform coating. We must apply the metallizing to a smoother surface. A lacquer film provides such a surface. The lacquer will be sprayed onto the screen material. Jets of water are used to prevent any lacquer being deposited on the sides of the tube. Again, the tube is dried. We will now deposit an extremely thin layer of aluminum on top of the lacquer film. This is the tungsten heater, which will vaporize a pellet of pure aluminum. A shield is placed around the heater to limit the spread of the metal vapors. The tube envelope is inverted over the heater unit. Plastic shields are placed in position. Vacuum pumps quickly remove most of the air or gas within the tube. A sensing coil with high-frequency energy connected to a meter will monitor the thickness of the metal film as it is being deposited. The temperature of the tungsten heater is increased. The aluminum is vaporized and immediately is deposited on the cool face of the tube. Here we have produced an accurately controlled metal film only a few microns thick. A solution of graphite particles called DAG is painted on the interior of the envelope to make contact with the resistive helix and the connecting terminals. The lacquer has accomplished its purpose, so now it must be removed. We cannot permit it to remain in the finished tube. It will be oxidized or burned out during further processing, leaving the metal film in direct contact with the phosphor. The final step in the preparation of the glass bottle or envelope is the baking or burning out of the lacquer and all volatile materials. The traveling oven heats the tubes to 420 degrees centigrade, almost their melting point. Then they are slowly cooled to anneal the glass. We are now ready for the final step in the assembly of the tubes. The gun unit is joined to the glass envelope. This is an automatic sealing machine or vertical sealer. The neck containing the gun assembly is clamped in position. The glass envelope is accurately aligned. Flames preheat the glass at the point of the seal. These hot flames quickly soften the glass. The two parts are brought together, fusing the glass. The glass is annealed at a lower heat to relieve any stress. The assembly is complete. Some of the tubes are handled one at a time on horizontal sealers or glass lathes. The gun is clamped in the chuck on one end of the lathe. The bottle or envelope is aligned to the other chuck. The glass is molten now. The parts are brought together. The seal is permitted to cool slowly. A high degree of operator skill is needed in sealing these tubes. The tubes are now positioned on the vacuum pumps. This is one of the most critical operations in the whole process. An induction heater coil around the neck will heat the gun parts to a red heat to help drive out gas trapped in the metal. The heater leads are connected to a voltage source. A cover containing heating elements or oven is partially lowered over the tubes. The pumps are started. A high-frequency spark coil checks for vacuum leaks. The oven surrounding the tubes heats the glass to almost its melting point to help drive off gas. Each pump station consists of a mechanical pump, an oil diffusion pump, and a charcoal cold trap. Most early failures of cathode ray tubes can be traced to a slight amount of gas remaining within the tube, which destroys the active oxide coating on the cathode. Extra care and extended bumping time will assure maximum tube life. After the ultimate vacuum of about 10 to the -7th millimeters of mercury has been reached, an extra heating element around the glass stem softens the glass and pinches off the seal where the tube is joined to the pumps. The work is almost finished. A few more operations are needed to complete the manufacturing of a precision cathode ray tube. The base is coated with cement and the leads are installed. The leads are trimmed and soldered. A heating unit cures the cement. Any residual magnetism is removed by passing the tube through a high alternating current field. The alignment of the faceplate is checked. The manufacturing process is finished. The tube is complete, but it still will not operate. First, the cathode must be activated. This is done by operating the heater at a high voltage for a short time and drawing current from the other elements. A precision product starts with careful engineering to high standards. To build such a product requires a combination of quality ingredients assembled with care and accuracy. Careful inspection during each step helps assure precision. No step is more important than the final testing. Every tube is instrument checked. It is checked under the actual conditions of operation. It must meet the exacting standards set by the designer. Uniform high quality can only be assured by rejecting and destroying any tube which does not meet these standards. The manufacturing operation has been performed with care. The materials used were the best obtainable. The tubes have passed each exacting test. They are now ready to operate, but it's still possible that some defect in processing or material may show up during extended use. Sample tubes from each batch are placed on an accelerated life test. These tubes will be operated until they fail at currents and voltages much higher than expected during normal use. A chart is kept on each tube, and readings are recorded at regular intervals. Any defect remaining in the tube will show up under this operation. Any early failure of the sample tubes during the test will be reason for the rejection of the entire batch. A lot of planning and a great deal of work has gone into the manufacturing of these tubes. It is with pride that we install this precision cathode ray tube in an oscilloscope bearing the Tektronix label.